In this video, we will review what aldosterone escape is in primary hyperaldosteronism, the renin-angiotensin-aldosterone system, the role of aldosterone in sodium and water conservation, previously proposed mechanisms of aldosterone escape, and the currently accepted mechanism of this pathophysiologic state. Aldosterone escape has been applied to two pathophysiologic states encountered in the practice of endocrinology. The first is the classic aldosterone escape of primary hyperaldosteronism. This phenomenon was first described in patients with Cone syndrome, which is an aldosterone-producing adrenal tumor associated with hypertension. Another form of aldosterone escape has been described among patients with heart failure treated with angiotensin-converting enzyme inhibitors. The latter is somewhat of a misnomer and may be better termed aldosterone breakthrough and will be discussed in a future video. In order to understand aldosterone escape, we will need to first review the renin-angiotensin-aldosterone axis. Renin, a protease enzyme, is the rate-limited enzyme of the renin-angiotensin-aldosterone axis. In the kidney, renin is synthesized by the juxtaglomerular cells, which are a group of specialized epithelioid cells located along the length of the afferent arterioles just at the entrance of the glomerulus. Juxtaglomerular cells are an important part of the juxtaglomerular apparatus. This illustration shows the components of the juxtaglomerular apparatus. It is composed of the macular denser cells in the distal convoluted tubule, juxtaglomerular cells present in the entire glomerular vasculature but more prominent in the afferent arteriole, and finally the afferent arteriole of the glomerulus. Next, we will take a look at the triggers of renin release in normal physiology. A change in sodium chloride load presented to the macular denser cells, which are a group of 15 to 20 cells in the distal convoluted tubule, influences the eventual release of renin from the juxtaglomerular cells. The macular denser cells are primarily sensors of sodium load, which relay their information regarding the sodium content of the urine to the juxtaglomerular cells. For example, a high sodium load in urine inhibits renin release from the juxtaglomerular cells, whereas a low sodium load stimulates the release of renin. A change in blood pressure detected at the afferent arteriole also controls renin release by the juxtaglomerular cells. In the setting of hypotension, low tension in the afferent arteriolar wall activates stretch-sensitive baroreceptors lining the afferent arteriole. This increases the release of renin by the juxtaglomerular cells, which ultimately enhances sodium conservation and the maintenance of intravascular volume. Finally, activation of beta-adrenergic sympathetic nerves terminating in the juxtaglomerular cells promotes renin release as well. This is because juxtaglomerular cells contain beta-1 adrenergic receptors on their cell surface. Next, we will review the role of the rate-limited enzyme renin in the renin-angiotensin-aldosterone axis. Renin catalyzes the conversion of angiotensinogen, the renin substrate produced and secreted by the liver, to a decapeptide called angiotensin-1. Angiotensin-1 has no biological action by itself, but it is the substrate for another endothelial cell-associated peptidase abundant in the human body, but primarily localized in the pulmonary vasculature, called angiotensin-converting enzyme, ACE. ACE cleaves the terminal dipeptide of angiotensin-1 to generate an octapeptide known as angiotensin-2. Furthermore, there is an isoform of angiotensin-converting enzyme called ACE2, which catalyzes the conversion of angiotensin-1 to an additional peptide known as angiotensin-1-7, which binds a vascular endothelial receptor known as MAS. Angiotensin-2 exerts its biological actions by binding to a family of surface transmembrane receptors widely distributed in the human body, known as type 1 and type 2 angiotensin-2 receptors, AT1 and AT2 receptors. Activation of AT1 receptors by angiotensin-2 results in the contraction of vascular smooth muscle cells, which increases peripheral vascular resistance and elevates blood pressure. These effects are partially counterbalanced by AT2 receptor activation by angiotensin-1 and MAS receptor activation by angiotensin-1-7, which results in vasodilation. In addition to the regulation of vascular tone, angiotensin-2 stimulates sodium reabsorption directly in the distal convoluted tubules of the nephron. Also, angiotensin-2 indirectly augments the production from the adrenal cortex of aldosterone, the most potent mineralocorticoid hormone that regulates sodium-potassium exchange in the collecting tubules of the kidney. Angiotensin-2 enhances the activity of the peripheral sympathetic nervous system and also promotes ADH secretion by the posterior pituitary gland. ADH then stimulates water reabsorption in the collecting duct. So how does aldosterone promote water and sodium conservation by the kidneys? This illustration shows a distal renal tubular cell. Aldosterone, a lipid-soluble steroid hormone, diffuses through the cell membrane of the ductal epithelial cell and binds to the cytosolic mineralocorticoid receptor. The aldosterone mineralocorticoid receptor complex is then translocated into the nucleus, where it attaches to hormone response elements required for the transcription and translation of the epithelial sodium chloride channel and sodium-potassium adenosine triphosphatase, sodium-potassium ATPase. The epithelial sodium chloride channel and sodium-potassium ATPase both play an active role in sodium reabsorption from the filtered renal sodium load present in the collecting duct and distal convoluted tubule. The net effect is a transfer of sodium from the apical to the basolateral side of the renal tubular cell. Aldosterone also promotes the expression of renal outer medullary potassium channels. The insertion of renal outer medullary potassium channels on the apical membrane facilitates potassium and hydrogen loss. In this model, hyperaldosteronism increases sodium and water reabsorption while promoting renal potassium and hydrogen ion losses. Consequently, hyperaldosteronism promotes plasma volume expansion, hypokalemia, and metabolic alkalosis. Plasma volume expansion increases renal blood flow, which decreases renin and angiotensin-2 production. Increased peritubular capillary hydrostatic pressure facilitates the flow of sodium from the interstitium back into the renal tubules. Natriuresis. In addition, stretching of atrial myocytes causes the excretion of atrial natriuretic factor, ANF. Atrial natriuretic factor then promotes the excretion of sodium despite hyperaldosteronism. Next, we will review the role of Stalin's forces in the pathophysiology of aldosterone escape. Under normal physiological conditions, sodium and water are reabsorbed from the renal tubular lumen and transported into the interstitium. Stalin's forces subsequently define the gradient of movement of sodium and water from the interstitium into the peritubular capillaries and subsequently the systemic circulation. It is worth noting that hydrostatic pressures across the renal tubules, interstitium, and peritubular capillaries are balanced in normal physiology. As a consequence, oncotic pressures dictate the flow of sodium and water. Because protein is much higher in the peritubular capillary compared to the interstitium, sodium and water are transported from the interstitium into the capillaries via oncotic forces. Conversely, in the setting of hyperaldosteronism, plasma volume expansion results in an overwhelmingly high hydrostatic pressure compared to the oncotic pressure in the peritubular capillaries. This pathophysiologic shift in Stalin's forces promotes the backflow of sodium and water from the interstitium into the renal tubular lumen. This is a form of pressure natriuresis, an adaptation that prevents hypernatremia and fluid retention or edema in primary hyperaldosteronism. I hope you found this video on aldosterone escape informative. If you want to see more of our videos about endocrine pathophysiology, then hit the subscribe button. Do not forget to click the bell icon so you will be notified when future videos in endocrinology are uploaded. Thanks for watching.